I hope you can hear me now. Okay. So, which algorithm did we attempt last? Yesterday, we have seen two algorithms. Which is the first one? Which two algorithms have we understood yesterday? Highest response ratio next and feedback based. True. Which one is non-preemptive? Yes. And what about feedback based? Is it preemptive? When do you preempt that? On arrival of a new process or at particular time duration? After, not at arrival, but after fixed time quantum, after fixed time duration, whatever you say, we will be preempting that. So whenever any process enters, it will be kept in RQ0, ready Q0. There are multiple ready queues. Whenever we are preempting that, it will be moved to the next queue. On subsequent preemption, it will be assigned lower priority and so on. That is what we have seen yesterday. This is the example or standard example which we have solved using time quantum 1. And we were getting something like this. Please look at this diagram. Are we getting this? B, C, sorry, B, A, C, B, D. Look at this. Are you getting this activity? Okay, Devansh. Okay. Others? And please calculate the turnaround time based on that, then average time. Then this is response ratio or normalized turnaround time, whatever you call it. Calculate that as well and match. Is it like this? I'm giving you one moment here to think over this and ask me if you have any doubts, because this is the simple feedback scheduling. Then we are going to see one variant of this, one version of this soon. So this one has to be very clear so we can understand and appreciate the next one. If you have any doubt in this, feel free to ask me. So let us quickly revise. If there are 5 queues, then in the first queue, there are 5 processes. I'm repeating, there are 5 queues. And in all the queues, there are 5 processes. Let us say there are total 25 processes. There are 5 queues. And in each queue, there are 5 processes. So out of this 25 process, which one will be given preference now? In RQ0. In RQ0, there are 5 processes. So which one will we select randomly? Yes, first come, first serve. Whichever is the oldest one, that we will select. Yes, first come, first serve. So whichever is the oldest in RQ0, that we will select. Then the next in RQ0, then the next in RQ0, and so on. Once it is over, we will go to RQ1, then RQ2, then RQ3. In all this, it is going to be first come, first serve. While in the last queue, the lowest priority queue, which algorithm do we follow to execute the processes? Round robin. Then we follow round robin. Perfect. So now, everyone, is this example clear? Now, can you tell me what is limitation of this algorithm? Or what do you think we can criticize it bit? Or is it biased towards any processes? Or is there any shortcoming of this? That is what I'm asking. This is preemptive algorithm. We have many queues to manage. That is one thing. Queues are to be managed. That means your overhead might be high. Your overhead might be high. Apart from that, can you think of anything? Okay, under which circumstances this algorithm is usually used? Can you tell me? Feedback algorithm that is used when there is a particular situation under which this is the most suitable algorithm. When do we use this? Yes, when service time is unknown. Yes, Vimal, nice. When we know the service time, that how much time will be required or length of the process. When it is known to us, then we have many algorithms, shortest process next or shortest remaining time or other algorithms. But whenever it is not known, then probably you can go for first come first serve or round robin. And both of them, round robin is okay if the time quantum is sufficient long enough. But in first come first serve, that might be uh, doing injustice to the short processes if they are at the end. While in feedback based, we are trying to make sure that short process will be executed first and longer one will keep moving in the lower queue and eventually they will be completing later on. So yes, switching will be there. But Abhi, switching will be there even in case of shortest remaining time. When we say shortest remaining time, then each time I'll have to calculate how much time is left. And then we will do switching. So calculation and switching, both of that will be there in that case. Even in highest response ratio next. First we will calculate the ratio, then we will say which is the higher ratio, and then we will select. And whenever each process is over, we are going to do that exercise again and again. So that is also computationally expensive and time consuming. Here we are not going to do any calculation. So in calculation time will not be there. But then the trade-off is more number of queues are to be managed. And first you will be going in the higher priority queue. If there is there, then quickly you will be picking it. So scanning time is not much in this scenario, if you can understand this. Scanning time or computation time is not high in feedback based as compared to shortest remaining time or highest request ratio next, or even for that matter shortest process next, where you will have to scan the entire queue to know that which one is the shorter process. While here you have to just check the first queue. Is there any process? Yes. Then the first process or the oldest process, whatever you call it, pick it, execute it. If the queue is over, then you will be going for the next queue and so on. So switching time will be there, but switching time would be there in any preemptive algorithm, that based on what is our quantum time. That is where we decide the quantum duration. The time quantum, if it is very short, then it will be very high. If there is longer sufficient, then context switching time will be saved. But then uh, some processes, let us say CPU bound processes, will be given more resources execution time as compared to IO bound. But that is story for the different matter. What I wanted to hear from you in the limitation is, this is punishing longer processes because each time it is preempted, it is going in the lower queue, then again in the lower queue and lower queue. And if new processes are coming, then the lower queue, they will be executed at the end. Do you agree with that statement? That this algorithm is punishing the longer processes. Yes. So now there is one version of this. So in feedback analysis, this longer processes completion can be stretched out alarmingly. It may take very long. And even starvation can occur if we are having new jobs coming frequently, because whenever new process come, we keep it in RQ0, then it will be in RQ1, then it will be in RQ2. And if our older long process has already reached to RQ7, then probably it will be taking much time. And before that, if already new job arrives, then again we are going to give that priority. So starvation may take place if the new jobs are keep coming in. So what is the solution to this? So here, this is a simple and elegant solution proposed, that preemption time can vary according to the queue. What have we done so far? Regardless of which queue we are working with, always time quantum was 1. That is what we have attempted in the previous version. In the basic plain version, what we have done? That from the first queue, the queue is equal to 1. In the second queue, same. In the third queue, same, and so on. Rather than that, here they are suggesting that lower queue will be getting the more execution time, because lower queue will not be executed frequently. Like R0 will be executed frequently, then R1, then R2. R3 will be given lower priority, R4 will be given even lower priority. So it is pretty unfair that in RQ0 also you are giving one time quantum, and RQ4 also you are giving one time quantum. So what they are suggesting, that time quantum can be decided based on which queue we are dealing with. So if it is ready queue 0, then 2 raised to 0, that means 1, time quantum will be 1. But if process is picked up for execution from RQ1, then time quantum 2 would be there. If it is in the third queue means RQ2, because we are starting with 0, 1 and 2, then it would be 2 raised to 2. That means for 4 time quantum, whenever its turn comes, at that time for 4 time quantum it will be executed. So I hope you can see what we are trying to do here, that the lower priority queue, where probably our longer processes are there, we are trying to allot its more time. Whenever it times come, we will execute that for more time before moving that to the, before preempting and moving to the lower one. So this way we can do some justice to longer processes. Yes, still starvation is possible. If it is very long, then starvation is possible. But still, if you see, it is far better than the earlier one. Like if you are talking about 7, if your uh, service time was 7, then what would happen? In the plain example, in the first one it got 1, then it was preempted. In the second one, it was one executed for one time unit, then it was preempted. Then in the third one it was executed, then preempted. That means 7 times it will move to the lower one, and when 7 queues are executed, then only that process will be over. While here in the first queue 1 duration will be given, in the second one 2, in the third one 4. That means just in 3 queues its time would be completed. In the fourth one it would be 8. That means 8 plus 4 plus 2 plus 1. I hope you can understand the difference. The earlier one was punishing the longer queue drastically, while here it is going to do much better. And if the process is really long, then yes, there is a possibility of starvation. But it is not so severe, or rather we can say degree has been reduced considerably here, because as it is moving to the lower queue, it is also increasing the time quantum exponentially. Does it make any sense to you? Others, apart from Priyank, what do others think? Okay, so I hope you can agree this, and we can verify the same using an example. Just a second. Okay, so I don't want to show you this. Let us solve the same example again using this approach, please. This example only. Can we solve using this approach, where our time quantum varies based on which queue we are picking up processes from? Queues? No, let us say take as many queues as you want. Okay, we are not having any restriction in queue here. Take as many queues as you want. Keval, we are going to solve this example using variable time quantum. The example which we have done, in that we have assumed time quantum to be 1. Doesn't matter from whichever queue we are picking it, time quantum was always 1. While here we are saying that in the first, the time quantum is based on 2 raised to I. From which queue you are picking up the data, that will be deciding the time quantum. Let me show you the equation. This. Time quantum is 2 raised to I. I is, which queue is this? Is it clear, Kevin? Kevin? Yes, Yes, I is starting. Were you absent yesterday? Yes, I is starting from 0. Yes, yes. I is starting from 0. Okay, all of you please attempt the example. So first I want you to draw the diagram that which process will be executed in which time unit. Then I want you to find out the response time, average response time, turnaround time, average turnaround time, normalized turnaround time, and average normalized turnaround time. These are the parameters which I'm expecting you to calculate. Please try to follow cues like this. Utilize as many cues as you like, or rather as many cues as are required. Okay, nice. Let us wait for 2 or 3 more people to complete it. Can you tell me the finish time of A, B, C, D, E? Complete time of this processes? I say some difference in the answer of Keval and Yash. Others, please pay attention to your book only. In Priyank's answer is even different. So all of us are getting different answers. And that is perfectly fine. Of course, the answers, all of these are not correct. Maximum one of this could be correct. But others, please keep doing. I'll ask after a while. Meanwhile, why don't you check your example once again? Keval, Yash, Priyank and Divan. Okay, let us please take 1 or 2 more minutes and let others to cope with us. Yes, A is not completed at 3. So Divan, Ronak, everyone who has said that A is completed at 3, please check it again. A gets completed at 4. And subsequently, other processes might also be impacted. Okay. So please, all of you check it again. I hope all of you understood the algorithm. Is the algorithm clear? Just there is one variation. It is same as what we have done yesterday with the varying preemption time. Preemption time or time quantum, whatever you say, is no more fixed. That depends on the queue. Which queue you are picking up the process from, according to that, our time will be decided. The higher priority queue will be having the lower time. The lower queue will be getting the more processing time, so that we are going to not punish longer processes exponentially or for the very long time. That is the idea. Okay, let me reveal the answer. Are we having like this? I will wait from 51 to 70. Roll numbers 51 to 70 to confirm. Okay. See, B has arrived at 2. So B is kept in the queue RQ0. On arrival, we are always having our process in RQ0 or the highest priority queue. And time quantum is 1 here. Here it is 2, 4. If there was RQ3, then time quantum would have been 8 here, 8 there, and 16 and so on. So here time quantum is 1 only. That means after executing A from 0 to 1, we were ready to preempt it. But because there is no another process available, we are again executing A. Now at 2, B has already arrived. So A will be moved to the next queue and B will be executed there. Priyank, is it okay? I think it was the case even yesterday. Priyank, you may unmute yourself and ask me a doubt if I'm not getting it.
Hello, ma'am.
Yes.
For after running of A for one time period, A is moved to RQ1. So execution time is 2 raised to 1. So it is 2.
No, it was not preempted. See here, actually, it was not preempted because there was no other process. So preemption was not
Yes,
done.
ma'am.
It was it was continued. Whenever
Okay.
any process is available, then only we'll preempt it.
Okay, ma'am.
Okay.
Got it.
Now, Keval, yes, let us look at your query. D is arrived at 6. D arrives at 6. Okay, let me look at the example. Yes, D arrives at 6. So, what do you say? No, we don't need to stop B at 6. If B is executing here, let us say B is picked up from this queue here, then time quantum is 2. Then for 2 it will execute, and whenever its time is over, at that time we will see that which is in this RQ0. So now D is there. So we will pick D. Here preemption is not on the arrival of the processes, but preemption is whenever its time is over. Okay. Others 51 to 80. Okay, Palna. Thank you. So you are getting this. Others 51 to 70, I'm getting only one confirmation. I need at least 6 to 7 confirmations that you have got this. $51 to 70 આવ્યા છે? આવ્યા છે તો જાગે છે? અને જાગો છો તો સાંભળો છો? Okay, channel. Have you got this channel? Or your answer is slightly different than this? I hope I'm not rushing you. Am I going too fast? That is okay, channel. Have you understood the mistake now? Could you figure out what the problem was? And next time, will you be able to rectify on your own? Okay, great. Others, I hope I'm not going faster. Am I? I'm intentionally trying to be at the moderate speed. Should I further slow down? Okay. So others, okay, any one of you, have we understood this properly? I'm not going to give you any other example for this. I'll be happier if girls answer. I'm happy with boys as well. But if any girl confirms, and if you have any doubt, then also I would be just fine. If you ask me doubts, then also I'll be equally happy. If you want to make any observation and discussion, then also that is fine with me. Okay. Others? Neville and Riddhi. Neville and Riddhi. Is your answer same as this or different? I'll wait for either Neville or Riddhi to respond. Friends of Neville or Riddhi, they can ask them to come out of hibernate. Okay, Riddhi, thank you. Here you are. Okay, thank you. So, do you have any doubt, Riddhi? Great. So, I take that this is fine. I assume that this is fine with all of you. So, are we getting this turnaround time in this normalized response ratio? Great, Kaushal. So, now as someone rightly said, that we may still have starvation. In spite of doing this, if the process is really, really long, then we may still have starvation. If the process is long and the new processes are coming in, then what can be the solution? The solution can be that if any process is spending certain amount of time in the queue, then we may promote that process in the higher priority. The another variant can be implemented like this. Like if one process has been waiting for some X amount of time which we have decided, then it will no more waiting in that queue only. It will be migrated to the upper queue, to the higher priority queue, so that chances will be upgraded. Again, it will wait there for some amount of time, and if time is it is not given the execution, then again it might be moved to the upper process. So priority is not going to be fixed, but it will be variable based on how old the process is, how much time you have waited. Based on the waiting time, we may decide the priority, we may change the priority, and then we can try to avoid the starvation. Does this idea appeal to you that this will work, right? Because whenever we are waiting for the longer duration, and if still it is not getting the execution time, we are increasing the priority so that it will be given the time. If it is still not working, then again it will be moved to the upper queue and so on. So that's it about feedback. Now there are some other scheduling algorithms. Very quickly we will be completing them all today. So first I'll give you just idea. Afterwards we will solve the examples. We can have priority scheduling. It can be preemptive or it can be non-preemptive. So far we had just arrival time and the service time of the process, name of the process, arrival time and service time. In priority based scheduling, we can have priority as well. Okay. And here we are assuming that lower the priority, better it is. So when P1 arrives, at that time, we will look here. Let us say first we are working with the non-preemptive version. In the non-preemptive version, can you solve this example? For non-preemptive version, I just want you to give me finish time for all the processes. So once you are completed, let me know. Based on the priority, we will decide who gets the resource. Here priority, lower the number, better it is. That is what we are assuming for this example. And how will you break the tie? If you think that two are having the same priority, which is not the case here. Here the priority number are different. But in case if the priority is same, then yes, first come first serve. Unless anything is mentioned, you will go for first come first serve, or you will go for the process ID, the oldest process ID. That is going to be the older process. So that can be used. When will P1 be completed? Okay, 4. P2? P2 25 or 6? P2 6. Yes, P2 will be completed at 6. P3? 9. P3 9. Yes. The second column is yes. Okay. Ronak, what do you want to say? Highest priority means take first. Ronak, can you please rewrite that? Okay. Oh, P4. When will P4 be completed? Uh, do you want to say that which process will be executed? I mean, what is the criteria to decide which process will be executed? Is that what you want to ask, Ronak? Okay. No. There are two things. Like if it arrives at 0, then we will look at the priority. That what is the priority? I mean, if there is only one process, then we will not check any criteria. It will be executed. And here I said it is non-preemptive version. So for time duration, P1 will get the resource. Then we are checking when will it be over at P is equal to 4. So how many processes do we have? We are already having this processes available, right? So what will we see? We will look at the priority, and we said that lower the priority, lower the number, higher the priority is. Like 2, 4, 6, 8, 9, 10, and 12. That is how they are prioritized. The prior. Okay, fine, you understood that. So P4, you said would be completed at 21. P5, what about P5? 10. Okay, P6, 25, and P7, 16. All right. So 9, 10, 15. So here there is no, is the processor idle for some time? When you execute that, is that ever happen that processor is idle? No, it doesn't happen. Okay, fine. It is executing complete initially from 0 to 25. It is continuously in process. So now I think if you solve this example, then we can go for preemptive version, where what do you want to keep your time quantum? You choose the time quantum that you will preempt after q is equal to 1 or q is equal to 2 or 3. These are the three choices I'm giving to you. 1, 2, or 3. Yes, 1. Okay, let us go for 1. I thought you would make it interesting and say something else. Anyway, let us keep it 1 if you prefer that. So everyone is now working with this, where we are going for preemptive version with priority with time quantum 1. Start working. So can you tell me when is P1 getting over? P1 is getting over at 4? Okay. Okay. Yes. Then P2? P2 at 6. Yes. Then P3? 9. P4? 21. P5? 10. Yes. P6? 25. And P7? 16. Aren't you giving the same answer as the earlier one? Is it same or different? Then do you think whether it is preemptive or non-preemptive will not make any difference? Is it so? Will priority scheduling always result into same flow regardless of whether it is preemptive or non-preemptive? Or it just so happens in this example? Come on, you can answer that. Only in some cases that will happen. Yes, only in some cases that will happen, only in this example. So can you tell me that what would be different in this example? Then preemptive and non-preemptive would result in the different execution of the processes. What changes if they were present in this example, then the answer would be different. Like yes, you can have here, let us just swap these two things, 4 and 2. Process 1, if it is having priority 4 and process 2 is having priority 2, then also it will be different, right? Here actually it happens that whenever any process is starting, then that is having the highest priority in all the processes which are going to come even in future. That is why it is never preempted. Like here, 8, it was P5 execution was already started before P4. So we don't have any issue here. But if P4 was initially started when P5 was not present, and then if P5 arrives, then naturally P4 will be interrupted, P5 will be given the resource, and likewise. Does that make any sense to you? I want new names to answer me. I'm saying repeatedly 15, 20 same names. So can I hear from different names? Others. Just a second. Hello, hello. Okay. So I hope this one is clear. Then let us go for I don't know why it is showing like this. Okay. Now, one of the algorithms can be longest process first. And example within 3 minutes, please. I'm not even going to explain this. I think you have matured enough with the scheduling algorithms that you will understand this. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . connected? Can you hear me? Okay, thank you. Great. So can you please give me completion time for all of them in sequence P1, P2, P3, P4 and P5? Can you give me the completion time for them? Okay. If you are all getting this, then that must be correct. If any one of you is getting a different answer, then feel free to write in. We will solve it. If you are getting a different answer, feel free to write it. If you all are getting the same answer, can I please give you the last one? So, longest remaining job first, but now we are going for a preemptive approach. So, what time quantum would you like to have? Tell me something other than one, please. Okay, thank you. Two. Let us go for two. Our time quantum is two, longest remaining job first, and we are going to go for preemptive approach. And this is the example. No one will answer, but only Chintan will answer in this one. Whenever he is done, Chintan will tell me. Chintan Solanki. Nice. We are waiting for Chintan to write. And I hope oh, okay. Chintan, can you hear me? Are you here? Okay, please continue. Yeah, please take your time. When is P1 being completed? P1 is completed at 3. Sure? 3 or 21? Yes, finish time. Okay, finish time Chintan is getting 21, 20, 17, and 12. Others? What are you getting? See, P1 is arriving at 1, not at 0. So, how would you interpret that? No, 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 Chintan. Don't worry about that. So, now this example was carefully chosen to make you think here only. Okay. So, I'm not going to answer you that what is the correct one here. I want you to open the book and read about it. And a very nice comparative table is given in the textbook of all the routing algorithms which you have learned. But you will be seeing here whether P1 will be completed at 3 or 21. I know that which approach each one of you is taking while working with this. What Chintan has done is like 0 to 2, this was done and then it was preempted because already here at 2, the higher or longer remaining job was taken. And others you have taken that from 1 it is assigning and then at 3 it is being preempted. So, anyway, think over this, search over this, and try to find out the correct answer. Apart from this one question, do you have any other questions? So that's it. Our scheduling algorithm chapter is over, and we have started with different type of schedulers. And before that, we have done the state transition diagram of processes, where we have talked about ready, then running, and blocked states. And there are different states in midterm scheduler as well. I hope you remember that. And if you have any doubt, please ask me. And this one is to be solved by you. And please open the textbook and read this chapter. So, anything else? Any one of you? Okay, then all the best for exams. I'll end the meeting now.